Chapter 7, Unit 3. The primary use for a distribution of sample means is to find the probability of selecting a sample with a specific mean. So let's look at an example of this. Suppose the population of scores on a math SAT test forms a normal distribution with a mean of 500 and a standard deviation of 100. If you take a random sample of n equals 16 students, what is the probability that the sample mean will be greater than m equals 525? Or restated, out of all the possible sample means, what proportion of them have values greater than 525? So from the central limit theorem, we know what the distribution looks like. First, we know that the distribution is normal because the population that they came from of math SAT scores is also normal. We know that the distribution has a mean of 500 because the population mean is also 500. And we know for n equals 16 students, the distribution has a standard error of 25 using the calculation, okay? So first thing you're going to do after that is you're going to find the z-score for 525. The way you would do this is you would make a picture and a table, and you'll notice that 525 falls at the z-score of +1. So then you're going to go to your tables, and you're going to look under z equals 1.00 in the tail, and you're going to find that the answer would be 0.1587 or 15.87% of the students. Now let's look at a z-score for sample means. So when we're talking about a z-score, the sign again tells you whether the sample mean is above or below the mean for the distribution, which is the population mean. And then the number tells the distance between the sample mean and the population mean in terms of the number of standard errors. So very similar to a z-score for single scores. The formula for the z-score for sample means looks like this. Z is equal to m minus mu over standard error. So when you're computing a z-score for a single score, we use standard deviation in the z equation. We're computing a z-score for a sample mean, we use standard error in the equation. So let's look at another example. A sample of n equals 4 scores is selected from a normal distribution that has a mean of 40 and a standard deviation of 16. What is the probability of obtaining a sample mean larger than m equals 42? Step 1 is always to compute the standard error. We cannot make our table until we have a standard error. Step 2 is to make the table using the standard error. So again, we used a mean of 40, and we used a standard error of 8. And then we're going to draw a line at m equals 42. Notice that's not on the table. So we're going to have to calculate a z-score. We can do that using our equation. Put in the numbers we found, and you should find z equals 0.25. Okay, and in this case, we're looking for a probability of a sample mean larger than that. So you would color to the right side of the line, and that would be a tail. So you'd look in the tail column in your table for z is greater than 0.25, and you would find 0.4031. So your conclusion would be that the probability of obtaining a sample mean larger than m equals 42 is 40.31%. Here's example 3. Suppose the population of scores on the math SAT forms a normal distribution with a mean of 500 and a standard deviation of 100. Using a random sample of n equals 25 students, what is the exact range of values that is expected for the sample mean 80% of the time? Well, before you can do anything, you need to find your standard error, and that's 20. You can actually go ahead and draw your table, but remember this time you can't put values in. You do not show z-scores for problems that only start with percentages. So what we can do is the middle 80% of the time, we can split it into two different parts. So you're going to draw a line down the center, and 40% is going to be on the left and 40% is going to be on the right. And then you have to also keep in mind that the p-value for 40% is p equals 0.4000. So you're going to locate in column D a p-value closest to 0.4000, and you're going to find that z equals 1.28. Remember, the tables don't tell you if your z-score is positive or negative. Only your picture will do that. So in this case, looking at our picture, we're going to determine that z is going to be positive and negative 1.28. So the next step we're going to do is we're going to solve for the mean. So given the z-score of negative 1.28, we put it into our m equation. And again, m is equal to mu plus z times standard error. And you should get a mean of 474.4. And then put the positive 1.28 into the equation, and you should get a mean of 525.6. So basically your conclusion is that 80% of all the possible sample means are contained in a range between 474.4 and 525.6. So if we select a sample of 25 students, we can be 80% confident that the mean SAT score for this sample will be within this range. Now it's your turn. Learning check problem 1. Pause the video, see if you can solve the problem. A sample of n equals 25 scores is selected from a normal distribution with a mean of 70 and a standard deviation of 20. If the sample mean is 78, then what is the z-score corresponding to the sample mean? Step 1, going to find your standard error. I found 4. Step 2, you're going to make a table using the standard error. You're going to draw a line at m equals 78. From the table, you can tell that z is equal to 2. And we can verify that using the z equation. We still get 2. So your answer would be D. Learning check problem 2. Again, see if you can work it. A sample of n equals 4 scores is selected from a normal distribution with a mean of 20 and a standard deviation of 4. What's the probability of obtaining a sample mean greater than m equals 22? First, we have to find our standard error. I found 2. Next, we make a table using our standard error. Again, we use the population mean of 20, and we use a standard error of 2 to make our table. Draw a line at m equals 22. You'll notice from the table you get z equals 1. You can verify it using the z equation. You should still get 1. Go to the tables in the tail column because we want sample mean greater than m equals 22. So if we shade it to the right side of that line, that would be a tail. And you should find a probability is equal to 0.1587. So your conclusion is that the probability of obtaining a sample mean larger than m equals 22 is 15.87%. Here's learning check problem 3. A sample of n equals 4 scores is selected from a normal population with a mean of 40 and a standard deviation of 6. What is the probability of obtaining a sample mean greater than m equals 46? Again, you start with your standard error. I found 3. You make your table using your standard error. Draw your line this time at m equals 46. And we are concerned with finding a sample mean greater than 46. So you'd color to the right of that line. That would be a tail. From your table, you can verify that for m equals 46, z is equal to 2. You can also verify it using the z-score equation, and you still get 2. Step 4, go to the tables, look in the tail column, and you'll find the probability of 0.0228. So the conclusion for this problem is that the probability of obtaining a sample mean larger than m equals 46 is 2.28%. The answer would be D.